Hello everyone, in this video we'll discuss about conversion of a rigid body into two mass system with a correction couple. Now we have already discussed the complexities of the connecting rod in a slider crank mechanism. We have already talked about that why the inertia force of connecting rod, like the consideration of the inertia force is quite difficult because of the non-uniformly distributed mass and the motion of the connecting rod, the complexity in the motion of connecting rod, because a part of it is connected to a rotating body and a part of it is connected to a reciprocating body. So to consider this oscillatory motion, to consider the inertia effect because of this oscillatory motion is quite difficult. It cannot be done in with a simple or a general formula or in the normal ways that we do it for other types of system. Therefore, if we want to replace this connecting rod with a dynamically equivalent system which does not have a correction couple, we replace in a way that this connecting rod, I'll show you a separated diagram, that we replace it with a link, a massless link with 2 point masses, let's say M1 and M2, in such a way that the mass of the connecting rod M is equal to M1 plus M2. First condition, the center of mass of both the systems, they coincide, right? So they remain same. So this is the center of mass. And the third condition was the moment of inertia of both the systems should also be same, right? So if I is the moment of inertia of the connecting rod, for the new system, moment of inertia becomes, if let's say this distance is A and if this distance is B, so it becomes m1 A square plus m2 B square, which is equal to the moment of inertia I. So what happens in the real system when we are replacing this connecting rod with a dynamically equivalent system, the mass at the crank pin, it becomes, let's say, MA plus M2, and the mass at the piston becomes, let's say, MB plus M1, right? So the masses at the crank pin and the gudgeon pin, they increase because we are converting the the connecting rod into a system having 2 point masses at the ends with joined by a connecting link, a massless link, right? Now, we have already discussed that it is not essential that the positioning of the point masses should be at the end of the link, but in case of connecting rod, we are initially what we are doing is we are adding these masses at the ends. So part of the mass, it gets added to the crank and a part of it gets added to the piston. So we have already discussed that by converting a connecting rod in a dynamically equivalent system, we are adding masses at the crank pin and the gudgeon pin, right? Now, this crank, it is rotating at some angular velocity omega with some angular acceleration alpha, and it has got some torque, let's say T is the torque which is acting on the system. But because the extra mass, the extra load is provided at the crank pin, what happens? This extra mass, it increases the inertia effect of this crank or the rotating body. Now, initially, whatever torque or whatever alpha we were giving to the system, it was sufficient enough to overcome the inertia effect because of the already existing mass at the crank pin. But now, because we have added the mass, so it will reduce the angular acceleration, or you can say it will reduce the turning moment of the system, which is not desirable. We don't want the system to get affected while creating the dynamically equivalent system. So what we can do while creating this dynamically equivalent system, we can produce another couple, right? We produce a couple in such a way that this couple acts in the direction of the alpha or the torque or the omega, you can say in the direction of rotation of the crank, thus reducing the effect of the inertia torque or the inertia effect because of the addition of masses at the crank pin. So the idea is simple. there is some torque, some omega, some angular acceleration in the crank, which is enough to resist the inertia torque in the system. But if you increase the mass, the inertia force increases. Now you have to give some extra torque to the system to ensure that the motion does not get affected. So therefore, in the further video, we'll discuss how can we create a dynamically equivalent system in such a way that we can provide this extra torque to the system so that the effect of inertia torque can be minimized. And this torque is also called as the correction torque, right? Now see, what we have done is the same thing we have done. There is a rigid body with some mass m, the center of gravity g, and we have reduced this rigid body, which is a connecting rod, to a body having the point masses at its ends b and a, right? Which is at the crank pin and the gudgeon pin. So let's say this mass is ma and this mass is mb, and the distances of masses ma and mb from the centroid or center of masses a and b, right? So we know the equations, and okay, and we've also created one more dynamically equivalent system, and we have placed another mass d at certain distance small d from the center of mass g, and the placement of d is done in such a way that a and b both are dynamically equivalent systems, and d is also placed in such a way that it also creates a dynamically equivalent system with b, right? So if B and D, they form a dynamically equivalent system, they should satisfy the conditions for a system to be dynamically equivalent, which is the masses, the sum of point masses should be same as that of the original mass. So M is equal to MB plus MD. The moments about the centroid, they should be same for both the masses, or you can say the sum of the moments, it should be 0. So it is mb into b is equal to md into d. And the third, which is the moment of inertia, it should be same for both the systems. So it becomes I is equal to mb into b square plus md into d square. So these are the three equations which should be satisfied to create a dynamically equivalent system. And we say that yes, b and d, they are satisfying all these three equations. So if we take this equation 2, we can write this equation as md into b, right, is equal to md into d. So we can write this equation as md is equal to, we can take d on the other hand, so it becomes mb into b upon d, right? Now if we place this equation in equation number 1, this is equation number 1, so it becomes m is equal to mb plus, what is md? We have calculated here, right? We have derived here. So now in this equation you can take mb common, so it becomes 1 plus b upon d. You take LCM, so it becomes mb b plus d upon d. Now the same thing can be done from this equation 2. We can also write the equation for mb. So it becomes mb becomes md into d upon b, md into d upon b. And if we place this equation in equation number 1, so it becomes this mp is equal to m into d upon b plus d. And if we place the values of this md and mb in third equation, which is the equation for moment of inertia, so the equation becomes this, the mbd, it becomes common, and we get I, moment of inertia, is equal to mass of the rigid body or the connecting rod into b into d, where b and d are the distances of the point masses from the center of mass. And we know moment of inertia is mk square, where k is the radius of gyration. So k square comes equal to b into d. So this equation we'll use in the further derivation, or it may also be used while doing the numericals. And b plus d we are telling as capital L, which is the equivalent length, right? The length of connecting rod is small l, which is a plus b, because these masses a and b, they are placed at the ends of the connecting rod. So this distance b plus d we are denoting by capital L, which is the equivalent length. That means if you want to create a dynamically equivalent system, it is also possible if some point mass is placed at point T, which is at some distance small d from center of this mass. Because while creating a dynamically equivalent system, it is not necessary to place the masses at the ends. They can be placed anywhere, only what the conditions should be satisfied. So initially we considered that the masses B and D are the point masses which are creating a dynamically equivalent system for connecting rod. Now we'll consider masses A and B for the dynamically equivalent system. And the positioning of A and B is at the ends of the connecting rod, therefore L is equal to A plus B, which is the length of connecting rod. Now if these two masses, these 2 point masses, they produce a dynamically equivalent system, it should also satisfy all the three conditions, which is the mass, the sum of masses should be same, the moments about centroid should be same, and the moment of inertia should also be same. So from equation 2, we can say that MA is equal to MB into B upon A. Similarly, we can say MB is equal to MA into A upon B, right? So these are the two values that we get. And if we place these values in equation A, that means in this equation, we get two values. So MA can be written as M into B upon B plus A, which is, and B plus A is what? L. So MB upon L. And MB can be written as MA upon L, right? Now we'll take third equation, which is the equation for moment of inertia. So it becomes, and because in earlier case we have taken I, so in this case we'll say let the moment of inertia be I dash, right? So it becomes M into, so MB is what? MB is MA upon L. So it becomes MA upon L into B square plus MB into A square upon L. So we get, because A plus B is equal to L, so we get the value M into A into B. And initially for systems B and D, we got moment of inertia as M into B into D. Here it is M into A into B. So if we talk theoretically, the moment of inertia should remain the same, because if the moment of inertia for the rigid body is I, it should remain I for all the dynamically equivalent systems. But if we look geometrically, we know that A is greater than D. We have taken the positions in such a way that A is at the end of the connecting rod and D is at a position which is somewhere, near the centroid and somewhere away from the end of the connecting rod. So geometrically A is greater than D. If A is greater than D, this factor, which is the M into A into B, will automatically be greater than M into B into D. So that means for the system of for the system of point masses at the ends, the moment of inertia is somewhat greater than the moment of inertia of two masses placed at some other points except for the end point, right? In this case, we have taken B and D. So this change, or you can say this difference in moment of inertia, will produce a correction couple. And that correction couple we are denoting by delta T. So we can also say in other words that by taking masses A and B, we have increased the inertia torque from the actual value for the system, right? So the torque, correction torque is given by alpha C into I, and what is I? It is actually delta I. So the change, the difference in the moment of inertia, so it is MAB minus MBT, which becomes, MB is common, so it becomes MB alpha C A minus D. So if we add and subtract B in this equation, it won't make any difference. So it becomes MB alpha C A plus B minus B plus D, so which is MB alpha C into L, length of connecting rod, minus capital L, which is the equivalent length. Therefore, the direction of this correction torque delta T is in the direction of the angular acceleration, or we can also say that the direction of this torque is in the direction opposite to that of the applied inertia torque, because the reason of creating this correction torque is to reduce the effect of the inertia torque, right? So it will act in the direction of the reducing delta B, which is the angle made by the connecting rod with the line of stroke. So it will act if alpha is in this direction, right? If this is the direction of the rotation of crank, delta T will act in the same direction or in the direction opposite to that of the inertia torque. This diagram we can also see that L, the length of connecting rod, in this case the masses A and B are placed at the ends, and D is at a point where we can find the equivalent length L, which is B plus D. Right, now we also know that to produce a torque in the system, the correction torque, we have to apply two forces, two equal and opposite forces, and of course parallel forces at crank pin and the gudgeon pin, right? So let these forces be denoted by Fy. And to produce a torque, the forces are equal, opposite and parallel. So we are applying the forces at the crank pin and the gudgeon pin. So to find the turning moment at crankshaft due to this correction torque, so this turning moment Tc will become Fy, right? Because these forces, these equal and opposite forces Fy, they are producing this correction couple. So it will be Fy into perpendicular distance, which is r cos theta. And we also know that this delta T is equal to Fy into perpendicular distance, which is L cos beta. Now if this distance is L and this angle is beta, this will be L cos beta. And if r is the length of crank and this angle is theta, so it will become r cos theta, right? Let this be theta, so this becomes r cos theta. So from this equation we can replace Fy by delta T upon L cos beta. So we place in this equation Fy is delta T upon L cos beta into r cos theta, where theta is the angle which crank makes with the line of stroke. So the turning moment at crankshaft becomes delta T upon, so from here r we can take here L upon r cos beta, and we know L upon r is the ratio which is the length of connecting rod upon the length of crank, which is equal to small n. So we can write this L upon r as small n, and we have already discussed and derived the equation for cos beta can be written as 1 upon n under root n square minus sine square theta. So this n, it gets cancelled out. So the equation becomes delta t cos beta upon under root n square minus sine square theta. So while doing the calculations, this inner turning moment, because of the correction torque, it is subtracted from the inertia torque, because the direction, the sense of the correction torque is always in the direction opposite to that of the inertia torque. Now because we have added a mass of connecting rod at crank pin, so what happens, the weight here, because of this added mass, it also increases at point A, and this weight also produces a torque at the crankshaft. So this added mass, because of the connecting rod, is it produces a torque which is denoted by TA, and this torque is equal to force into perpendicular distance. So what is the force? It is actually the weight of the added mass, which is ME into G, and the perpendicular distance becomes this, which is r cos theta. Now in case of the vertical engines, one more inertia torque is added because of the weight of the masses at point B. So for vertical engines, the weight, the torque, because of the added weights, it will be force, which is mb into g into r sine theta plus sine 2 theta upon 2 under root n square minus sine square theta. This equation again we have already derived, which is it gives the turning moment due to the weight of the piston when we talk about the vertical engines. Therefore, the net torque on crankshaft is because of these 5 factors, which is the inertia force due to the inertia torque due to the inertia force at piston because of the inertia of the reciprocating masses, plus the masses because of the part of the connecting rod which is added at the gudgeon pin, the inertia torque because of the weight of the mass at the crank, which is added because of the connecting rod at the crank pin. This we have already discussed. The inertia torque due to the correction couple, The turning moment because of the weight of piston in case of the vertical engines, because the weight, everything it comes on the crankshaft, and the turning moment due to the force of the gas pressures. Now the net torque on the crankshaft is the algebraic sum of all these factors. This is only for the vertical engines. So this is how we find the net torque on the crankshaft, and depending upon the sense whether they are in the clockwise or counterclockwise direction, the signs they get changed, and this is how we can find the net torque or the total turning moment.